All right, so section 4.1 is all about maximum and minimum values. So basically, what we got to do in this section is we got to learn the difference between what's a local maximum or minimum and an absolute maximum or minimum. Yeah, we need to learn how to find critical values and or critical numbers and find the absolute maximum and minimum values for a continuous function on a closed interval. All right, so start off with a local maximum and a local minimum are basically, let's just draw a picture to demonstrate this. If I have a function and it looks like this, let's just suppose it goes like this, and suppose it looks something like that. All right, so, and then let's actually have it level off so it's nice and clear. So when I look at this, this point up here, that value is the absolute max, and this value down here is the absolute min. Now local maximum and minimums, well, I'm going to label those in green. That's a local max, that's a local min, that's a local min, that's a local max, that's a local min, and that's basically it. So sometimes they're called relative minimum or relative maximum values. Well, sorry. And then, so, and again, if you have one of them, it's a maximum. If you have multiple, the plural of maximum is maxima. The plural of minimum is minima. And then we use the word extremum to refer to a maximum or a minimum. So if I say extremum, that just means a max or a min, and the plural of that is extrema. So if we're talking about one, it's extremum. If we're talking about many, it's extrema. So find all absolute extrema of f of x equals sine of x. So just to refresh your memory, sine of x looks like this. And so notice we have an absolute maximum here, an absolute maximum here, and over and over and over again. Because again, if you look at it, it repeats itself, right? And then we have an absolute minimum here, 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 etc., and forever and ever as well. So the absolute max is 1, because that's that value right there, and the absolute minimum is -1. Now, just to be clear, these things are the y values. So these guys, when we're talking about local max and absolute max or whatever, those are the y values. We would say they occur at the x values. So this, like an absolute maximum occurs at, that happens at pi over 2, also happens at 5 pi over 2, also happens at 9 pi over 2, etc. And then similarly 3 pi over 2, 7 pi over 2, etc. So that's where they occur, but there's only one absolute max and one absolute min. It just hits it many times. So we have an absolute max of 1, absolute min of -1. It just hits it many times. All right, so a critical number of a function f is any number c. Now notice I bolded this in the domain of f, so it has to be f has to be defined at c, for which f prime of c equals 0 or f prime of c is undefined. So the derivative can be undefined, but the original number has to be in the original function. So let's take a look and find the critical numbers of f here. So first things first, we got to find f prime of x is equal to x cubed minus 8x plus 15. So we're going to set that equal to 0 because we're looking at where it's equal to 0 or it's undefined. Well, where is it undefined? Well, this is a polynomial. It's defined everywhere. So that's nothing to worry about. So it's just going to set it equal to 0, and we factor, and we notice x minus 3, x minus 5 will take care of the deal. So my critical numbers are x equals 3 and x equals 5. Example 3, find the critical values of this function. So if I look at this, f prime of x is equal to -1 over x squared using the power rule, right? We're thinking of that as x to the -1. So the -1 comes out in front, becomes a -2. So I get that. So where is that 0? Nowhere. Where is it undefined? It's undefined at x equals 0, right? Because that would be divided by 0. Now, is 0 a critical number? Well, remember, it has to be in the domain of f. So can I plug 0 in to my original function? Nope. No, I can't. So no, there are no critical numbers. So if f has a local extremum at a number, then at c, then c must be a critical number of f. So if I have a max or a min, like each of these points on my graph here, that in my original thing that I'm looking at here, let me even do a different color. So each of these points here, there, that must be, each of those x values must be a critical number. And then the extreme value theorem says that if f is continuous on a closed interval, then f has an absolute maximum and an absolute minimum in that interval. So if I have any, let's just draw a picture here. If I have any interval, say from a to b, so here's a, here's b, and here's suppose my function looks like this. So then notice I have an absolute maximum here and an absolute minimum somewhere in here. I don't know. I didn't draw it very nicely, but I must have an absolute maximum. Now notice it has to be continuous. The key here is continuous, and it has to be a closed interval. And the reason for that is if I were to draw this instead, like let's suppose I have an open interval. So let's just say it looks like this. So I pick an open interval there. Notice I do have an absolute minimum. It's right here. But I don't have an absolute maximum because, like, let's just suppose that we get at this, and this is at 1, and this is at 3. Well, it never reaches 3, right? It never reaches 3, so 3 isn't the maximum. It has to actually hit the value. But 3 is what's called an upper bound. We're not going to be worried about that, but that's what we call it because it can't get to 3 or any bigger. But there is no maximum value because if you pick 2.9 as your maximum value, well, I could have gone further. I could have picked 2.99. That's even bigger. Well, if you pick 2.99, then you might not pick 2.999. And so there is no number that the function actually hits that is the maximum it hits, right? I can't pick 3 because it never hits 3. And any number less than 3, I will actually exceed at some point. So that's why it has to be a closed interval so that this situation doesn't happen. All right, so so with that idea, if we have any continuous function on a closed interval, we should be able to find an absolute maximum and an absolute minimum. So we're just going to follow a little three-step process. 1, find the critical numbers of f. All right, so let's find that. So f prime is equal to 2x minus 6. Remember, the critical numbers are where the derivative equals 0 or it's undefined. Well, this is always defined, so we just need to find where it's equal to 0. 2x equals 6, x equals 3. So that's my answer for number 1. Number 2 says plug the numbers from 1 and the endpoints of the interval a, b into f. So we need to plug in 0, we need to plug in 4, we need to plug in 3. So f of 0, f of 3, f of 4. And we're just going to look for which one's the biggest and which one's the smallest. So when I plug in 0, I get 0 squared minus 6 times 0 plus 4. So I get 4. And remember, we're plugging it into the original function, not into the derivative. So f of 0 equals 4. F of 3 equals 3 squared minus 6 times 3 plus 4, which is 9 minus 18, negative 9 plus 4 is negative 5. And we plug in 4, and I get 4 squared minus 6 times 4 plus 4, which is 16 minus 24, which is negative 8 plus 4 is negative 4. So looking at this, we would say 0, 4 is the absolute maximum. And we would say 3, negative 5 is the absolute minimum. Now, just a reminder, if the value, the absolute max is 4, and it occurs, all right, so the max is 4, it occurs at 0. It occurs at x equals 0. That's kind of how you can think of it. But I'm okay with an ordered pair. whenever you write it. So you can write 0, 4, or you could just write 4. But I kind of like the ordered pair. Both are correct, but if it just asks what is the absolute extrema. But I like ordered pairs in general, so it just gives you a little bit more information, but it's up to you. So let's take a look at this one. So again, so 1, f prime equals 12x cubed minus 12x squared minus 24x, and we want to set that equal to 0 or where it's undefined. Again, it's a polynomial, so it's defined everywhere, so all we need to do is solve where it's equal to 0. So let's factor out a 12x, leave me with x squared minus x minus 2, and so I get 12x x minus 2, x plus 1. So my critical values are x equals 0, 2, and negative 1. So now I got to plug all of these guys in and the endpoints. So f of negative 2, f of negative 1, f of 0, f of 2, f of 3. Now I don't want you to think I'm just plugging in a bunch of whole numbers between negative 2 and 3. There's a reason for the ones I picked. And just by plugging in all the whole numbers isn't necessarily going to get the right solution every time, because these critical numbers don't have to be whole numbers. So don't take that as the result. So we're taking our critical numbers and our endpoints and plugging it in. Okay, so, and let me give a little bit more space down here. So f of 2. Actually, I can probably just do it down here. F of 2, f of 3. All right, so we plug in negative 2. And probably, we're probably going to want to use our calculators here. So here, let me pause and get my calculator out. All right, so I'm just going to do negative 2, store that as x, and then I'm going to do, again, we're plugging into the original function, so 3x to the 4th minus 4x cubed minus 12x squared plus 1. All right, so I got 33 for this one. Now let's go ahead and let negative 1 equal x, and then we'll plug that all back in again. So we get negative 4. Plug in 0. Well, that one's easy. I get 1 because all the first three terms all go to 0. Plug in 2. Go back and plug that all in again. I get negative 31. Then plug in 3. So I get 28. So look at the biggest number. 33 is my absolute max. This is step 3, what I'm doing right here. And then negative 31 is our absolute minimum. And that's basically all you need to know for this section.